So, welcome to my talk. I'm Eduardo. I'm a professor of statistics at the Federal University of Rio Grande do Sul, that's in Brazil. This is a joint work with my colleague Rafael Rigon and the student Luisa Borsato. She's a PhD student at the Institute of Mathematics and Statistics at the University of São Paulo. I'm going to present my latest piece of research, which is called a characterization of the strong law of large numbers for Bernoulli sequences. I'll share this file later so you can access the archive preprint here in this link. And let's go straight to the point. So our main theorem says that a sequence of Bernoulli p random variables, p is the parameter of unbalancedness, so to say, or probability of heads. So such a sequence, and not necessarily independent, will satisfy a law of large number type result if and only if you can find a latent sequence theta 0, theta 1, etc. of random variables which take values in the unit interval and for which two things happen. First, a certain independence decomposition is valid, so if you condition on the sequence of thetas, the original x's are independent Bernoulli random variables, but with distinct parameters given by the thetas, and almost surely the varthetas, the sample average of the varthetas, converge to P. So what this result is saying is that a certain sequence of coin throws will have the property of the proportion of heads converging to the parameter of unbalancedness, which is the P in the above theorem, if and only if these coin throws are conditionally independent, where you condition on a sequence of random parameters of unbalancedness, and these parameters satisfy themselves the law of large numbers. So the motto is, the strong law comes from latent factors plus independence. Or if you're more into dynamical systems, ergodicity is an assumption. So yeah, you could say that it's not possible to detect from data if a strong law result is valid or is a valid assumption or not, because you can always have latent factors driving the validity of the strong law. So the above theorem, it follows from a more general result which we prove in our paper, so I'm going to state it soon enough, but let me just discuss a little bit something that is related to this representation as an independent sequence. So we say that a sequence of random variables is exchangeable if the joint law of this sequence is invariant under permutations. So if you swap the axes in the joint distribution, so to say, you remain with the same law. But an interesting characterization of exchangeability is given by the Definetti and Real-Nardzensky, I don't know how to say that, Real-Nardzensky, and it says that a sequence of random variables is exchangeable precisely when you can find a random probability measure, let's call it psi, such that you can represent the conditional distribution of the axis as an IID distribution. So, for short, exchangeability is the same as conditionally IID. In view of that, we introduce the notion of a product disintegration, and we say that a sequence of random probability measures is a product disintegration of a given sequence of random variables if you can condition on the whole sequence of random probability measures, and then the original sequence of x's is an independence, conditionally independent sequence. Not necessarily IID, but independent. And you see that in this case, product disintegrations generalize the notion of exchangeability. So this is a natural generalization because it's what you get formally when you try to answer the question. What happens when the random product measure, which characterizes exchangeable sequences, what happens if I substitute that by an arbitrary random product measure? So basically that's what the concept of a product disintegration tries to capture. And then you can, with this concept in hand, you can restate our first theorem by saying that a sequence of Bernoulli random variables satisfies the strong law precisely if admits a product disintegration, and of course with the extra requirement that the product disintegration satisfies a strong law type result. So the stronger result, which I mentioned, it says that if you have a sequence of random variables and a given product disintegration of this sequence, then given any continuous function from the state space, real valued function defined on the state space of X, you have that certain limits, if they exist, coincide. It's not what's written here, but if, say, the sample averages of these guys here exists, then it coincides with the sample average of these guys here, and the other way around. So if the sample averages of these guys here, notice that T is here. If this limit exists, then this limit exists, and they obviously coincide. So it looks less attractive than the first theorem, but it's stronger. So the idea of proof for theorem 1 is actually quite simple. To get a sketch, to formalize it, you need results from disintegration of measures. It's not that easy to arrive at that. But for the if part, you can define a new random variable, call it zt, which is simply xt minus theta t. So remember that xt conditional on the whole sequence of var thetas. Xt has Bernoulli distribution with parameter theta t. So if I take the conditional expectation of zt with respect to the whole sequence of theta t's, I see that, well, this guy is measurable with respect to this sigma field, so it just gets out of the conditional expectation. You have this guy outside here, and then you have the expectation of xt given the whole sequence of thetas, and as I said, by definition, xt conditional on this sequence is Bernoulli with parameter theta t, so this conditional expectation is theta t. So conditional on theta t. The zt's are centered, they have expected value 0, conditional expected value 0, and they are independent because of the formula which defines product disintegrations. So what I'm saying is that conditional on var theta, the whole sequence of thetas, the zt's are independent, centered, and have a uniformly bounded variance. So conditional on theta, I can summon Kolmogorov's strong law to see that the sample averages of the zt's converge to their, of course, conditional expected value, which is 0 in this case. So certainly this expression is true, And if you take the expected value, the unconditional one, of course, then you see that the conditioning disappear because of the law of iterated expectations. And then you see that the limits in theorem 2 coincide. You could give this extra step. And yeah, that's it. The sketch is this. For the only if part is quite straightforward. You can have a look at the preprint. And well, that's it. I'm going to leave you with this quote from Seneca, which is an author that I like a lot. And I hope you have enjoyed this talk.